If you pick up just a piece of ordinary volcanic rock off the ground, it's heavy, it's brittle, and it's basically useless for anything other than, a paperweight.
Right, pretty much.
But a translated strategic business proposal from a company called Oildynamics LLC suggests that if you melt that exact same rock down and spin it, it becomes an aerospace-grade supermaterial.
Which sounds like science fiction, honestly.
It really does. I mean, we're talking about a material capable of replacing the steel backbone of modern cities, armor plating a military vehicle, and even insulating the fuselage of a spacecraft. Welcome to the deep dive.
Glad to be here.
Today, we're tearing into a massive, sweeping plan to establish an industrial cluster for what the proposal calls continuous basalt fiber, or CBF. They are targeting the Gulf Cooperation Council countries, the GCC, and Africa.
Yeah, and what's fascinating here is how this document isn't simply pitching, a slight upgrade to fiberglass or some new niche composite.
Yeah.
They are explicitly framing continuous basalt fiber as the future replacing metal. The sheer scale of ambition in these pages is staggering.
It's a huge claim.
Exactly.
Yeah.
I mean, they're looking at the foundational materials our modern supply chains and infrastructure rely on: steel, aluminum, heavy plastics, and outlining a blueprint to systematically replace them with a product pulled straight from ancient volcanic activity.
Okay, let's unpack this.
Yeah.
Because going from a chunk of solidified lava to a high-performance aerospace material requires a bit of a mental leap.
It does, yeah.
The best physical analog here is making cotton candy. You take solid sugar, you melt it down into a liquid, and spin it through these microscopic holes until it forms incredibly fine, flexible threads.
Right, the spun sugar.
Yeah, and the proposal basically describes a scaled-up, extreme version of that exact process.
Yeah.
You take raw, natural basalt rock, subject it to immense heat until it liquefies, and extrude it into continuous threads of stone.
Threads of stone. It's wild to think about.
It really is.
Yeah.
The result is a fiber flexible enough to weave, yet it carries the latent, immense strength of the Earth's crust.
Well, the cotton candy visual works, but you have to imagine doing it at roughly 1,500 degrees Celsius.
Oh, wow. Yeah, that's hot.
Right, and that temperature requirement is exactly what has historically made this material a complete nightmare to scale commercially. Melting rock on an industrial level requires a relentless, colossal amount of thermal energy.
Which usually means massive energy bills.
Exactly, and this is where the document really pivots from a scientific novelty into a highly aggressive business strategy. The true innovation Oildynamics LLC is bringing to the table isn't the spinning process itself.
Right, because that science has been around for a while.
Yeah, that foundational science has been established in research centers for years. The masterstroke is the energy source they plan to use, which is APG, or associated petroleum gas.
Wait, I have to push back on that setup for a second.
Sure.
Flaring gas at an oil well is notoriously inconsistent. We're talking about running a precision, high-tech manufacturing process that requires thousands of degrees of constant, uninterrupted heat.
Right.
Can you really power a localized aerospace-grade foundry on the variable waste gas burped up by an oil extraction site without, the whole system stalling out?
That variable flow is definitely the traditional bottleneck, absolutely. But the proposal addresses this through a fully integrated deployment model that actually stabilizes the feed.
Oh, okay. How so?
Well, when oil companies drill, APG comes up alongside the crude. Historically, it's a massive logistical nuisance and a huge environmental liability, which is exactly why you see it constantly burning off at the wellhead.
Right, those big flames at the top of the towers.
Exactly. By capturing that APG directly on site, stabilizing the pressure, and routing it straight into the basalt melting furnaces, they are essentially zeroing out their primary operating expense. They're utilizing an energy source that is abundantly available in the GCC's oil-producing regions and capturing it before it's literally wasted into the atmosphere.
So it's turning a massive environmental and financial liability into a localized power grid for heavy manufacturing.
Precisely. The document outright claims this synergy provides a record-low production cost, and the economic leverage becomes undeniable when you look at the market value of the output.
Let me guess, it's pretty high.
Oh, very. The proposal outlines that these finished basalt products command a market price ranging from $3,000 to $30,000 per ton.
For $30,000.
Yeah, particularly when it's refined into the highest tier aerospace-grade materials. So you have a highly valuable, highly specialized material being produced at a fraction of the traditional energy cost.
I mean, a $30,000 return on a ton of melted rock is phenomenal, provided you actually have heavy industries whose physical problems are expensive enough to justify the switch.
Right, you need a buyer.
Yeah. And looking at the first major target in the proposal, it's the very industry providing that cheap gas, the oil and gas sector itself. They want to completely replace traditional steel pipes with basalt composite systems.
Which is a massive undertaking.
It is, but using steel pipes for deep earth oil extraction is basically like using a sugar straw to drink scalding hot coffee.
That's a great way to put it.
The environment down there, the extreme pressure, the heat, the aggressive saline, the hydrogen sulfide, is actively trying to dissolve the container from day one.
The mechanism of failure with steel in those environments is just relentless. It's not just simple rust we're talking about. The steel is constantly assaulted by highly aggressive chemical compounds that compromise its structural integrity at a molecular level.
Right.
Oil companies bleed vast fortunes mitigating this. They apply extremely expensive anti-corrosion coatings, run constant diagnostic maintenance, and prematurely replace thousands of miles of infrastructure just to prevent catastrophic blowout.
And salt just avoids all of that.
Inherently, yeah. Basalt is a mineral that has already been subjected to extreme heat and oxidation within the Earth's mantle, so it is chemically inert in these environments.
It simply ignores the chemistry trying to destroy it.
It doesn't corrode, period.
By deploying basalt composites, an extraction operation eliminates the primary risk factor for pipeline failure and entirely wipes the ongoing costs of anti-corrosion protection off the ledger.
That structural immunity translates perfectly into the construction sector as well, from what I read. The proposal leans heavily into what they call the BARS system, which is continuous basalt fiber used as rebar.
Oh, the rebar application is huge.
Yeah, if you look at the climate in the GCC, relentless extreme heat combined with aggressive, highly saline soils, traditional construction faces a massive invisible threat there.
Concrete spalling. It is an infrastructural epidemic in coastal and highly saline environments. When you build foundations or bridges or highways using standard steel rebar inside concrete, you have to remember that concrete is inherently porous.
It's basically a sponge. Exactly. Moisture and salt inevitably wick their way in. And once the salt reaches the steel, the metal begins to oxidize.
And when steel rusts, it expands. It swells up to roughly 4 times its original volume.
Right.
Concrete has incredible compressive strength, meaning it can hold up a skyscraper, but its tensile strength is relatively low. So when that steel skeleton swells up inside, it literally blows the concrete apart from the inside out.
The structure destroys itself. Replacing that steel core with the BARS basalt system means you are embedding a skeletal reinforcement that won't react to that wicked in moisture.
Which solves the whole problem.
Exactly. The basalt rebar maintains its exact volume and tensile strength, securing a permanent structural reinforcement that drastically extends the lifespan of the infrastructure.
And I noticed that the moment you solve the salt problem for soil, the immediate next step is the ocean.
Naturally.
The proposal targets shipbuilding and marine infrastructure hulls, port facilities, offshore platforms. Basalt doesn't rot in salt water, dropping those massive annual dry dock repainting and maintenance bills to near zero.
Which shipping companies will love.
Right. And because the composite is exponentially lighter than structural steel, a ship's hull weight drops significantly.
And a lighter hull directly increases cargo capacity and fuel efficiency. It fundamentally shifts the operating margins of an entire shipping fleet.
It's wild.
And the document scales that exact same logic of longevity and flow efficiency to municipal utilities, too. We're talking about the critical, invisible veins of a city, water supply pipes, sewage lines, protective cable channels. The proposal promises a service life exceeding 50 years for basalt municipal pipes.
I mean, if you've ever had your neighborhood street torn up for 6 months because of a burst water main, you know exactly how expensive and disruptive traditional metal pipes are for city budgets.
Oh, absolutely. Metal municipal pipes fail for 2 primary reasons: external corrosion, which we've discussed, and internal overgrowth.
Oh, right.
Minerals and grime build up on the rough internal surface of metal pipes over decades, restricting the flow, increasing pressure, and eventually causing a blowout. Basalt composite pipes maintain a smooth, completely inert internal surface.
So things just slide right through.
There is no mineral overgrowth. The flow remains consistent, massively relieving the financial burden of constant municipal excavation and replacement.
Okay, so surviving aggressive soil, outlasting municipal water pressure, shrugging off ocean salt, that is all deeply practical foundational infrastructure.
Very foundational, yes.
But surviving the mud in the ocean is one thing. Surviving the absolute extremes of modern human technology is an entirely different tier of engineering. Here's where it gets really interesting, because the proposal dramatically shifts gears from heavy industry into the realm of high-tech and extreme environments, starting with what they label complex green energy.
Right. They highlight the manufacturing of ultra-strong blades for wind generators and load-bearing frame structures for massive solar energy farms.
Which sounds standard until you think about where these are going.
To understand the necessity here, you have to picture the deployment environments in the GCC and Africa. These green energy farms are often situated in vast desert expanses. The wind carries highly abrasive sand at really high velocities.
It acts like a relentless industrial-scale belt sander.
Exactly the issue. Traditional materials used for wind turbine blades, like standard fiberglass composites, suffer from severe microabrasive wear. The sand slowly degrades the resin, causing microfractures that eventually compromise the massive cyclic load-bearing capacity of the blade.
So they basically snap or just fall apart over time.
Yeah. But basalt fiber is significantly denser and harder on the Mohs scale. It is uniquely resistant to that shear sand abrasion, meaning the turbines can withstand the high repetitive stress of rotating in a desert sandstorm for years without requiring premature, really expensive blade replacement.
You're building a renewable power grid that doesn't get sanded down to dust by its own environment. But they push the material limits even further, explicitly calling out aviation and space and targeting those highly lucrative aerospace-grade materials we mentioned earlier. We're looking at fire-resistant fabrics and advanced thermal insulation designed to wrap the fuselages of aircraft and spacecraft.
The extreme thermal properties of basalt truly separate it from standard composites here. Because the foundational material was literally forged in magma, its thermal degradation point is exceptionally high.
It can withstand blistering heat.
It can, but in aerospace engineering, heat resistance is only half the battle. The governing metric of spaceflight and aviation is mass. Every single ounce of structure on a rocket or a commercial jet costs a premium to lift into the air.
The strength-to-weight ratio is everything.
The proposal heavily emphasizes that continuous basalt fiber composites offer a massive reduction in the structural weight of the fuselage and internal components, while maintaining or even exceeding the extreme structural strength of traditional aerospace metals. Shedding that weight directly translates to a massive boost in fuel efficiency, payload capacity, and overall operational safety.
It's the holy grail of aerospace design. But the source material also traces this rock down into the microscopic world electronics and electrical engineering. They specify the production of dielectric printed circuit boards.
Right, dielectric boards.
Now, maintaining a stable dielectric profile is critical because you need the board to reliably insulate the electrical paths, keeping the complex signals separate. The document claims basalt maintains extreme dimensional and insulating stability under severe temperature fluctuations and extreme humidity.
Environments where traditional plastics begin to warp and standard metals lose their insulating properties or begin to, sweat and short out.
Right, which destroys the electronics.
A basalt-based circuit board ensures complex electronics function flawlessly, whether they are deployed in a boiling, humid jungle canopy or the freezing, dry vacuum of the upper atmosphere.
Which brings us to the inevitable intersection of extreme physical toughness and environmental stability. The proposal dedicates a significant section to the defense complex.
Yes, it does.
They point specifically to the unique impact toughness of basalt fiber. They aren't just using it to insulate wiring, they are proposing lightweight composite armor, protective panels for specialized military equipment, and rapid deployment mobile fortifications.
The physics of basalt fiber make it highly effective for kinetic absorption. It isn't just a rigid plate that shatters under impact.
Right.
The woven fiber structure catches and disperses the kinetic energy of a ballistic strike across a wider surface area. The narrative for the defense sector is incredibly compelling.
Yeah.
You have a composite material light enough to keep an armored personnel carrier fast and agile, tough enough to absorb and dissipate kinetic impacts, and inherently fireproof.
It is wild to map out that life cycle. I mean, the same core volcanic material could be wrapping a municipal sewer line under your street, stabilizing the motherboard inside your laptop, and bolted to the exterior of an armored vehicle.
It's incredibly versatile.
But having all these incredible applications, drawing up this perfect world-changing blueprint on paper, it honestly means nothing if you can't actually build the infrastructure to produce it.
That's the real challenge.
You can't just mandate a new industrial revolution, flip a switch, and suddenly an entire region stops importing steel and starts spinning rock.
Yeah.
How does Oildynamics LLC actually plan to execute this massive regional vision?
If we connect this to the bigger picture, the execution strategy outlined in the document is just as vital as the thermal physics of the fiber.
Right.
The proposal relies heavily on a specific integrated model for implementation, the EPC model. That stands for engineering, procurement, and construction. In heavy industry, this is often referred to as a turnkey solution.
So they aren't just selling the GCC a catalog of spinning machines and wishing them luck.
No, not at all.
Yeah.
The client doesn't have to hire a separate architectural firm, a separate buyer for the heavy machinery, and a separate local contractor to pour the foundations. Oildynamics LLC proposes managing the entire life cycle of the factory's creation from the ground up. They engineer the layout, procure all the specialized furnaces and extruders, manage the construction, and integrate the associated petroleum gas feed directly from the local oil infrastructure.
They handle everything.
The document guarantees what translates to maximum fast deployment, ensuring the rapid stabilization of production capacities.
It's essentially a factory-in-a-box approach. They parachute in, build the facility, hook up the local flare gas, train the local workforce on the extruders, hand over the keys, and suddenly that specific region has an operational, continuous basalt fiber cluster.
That turnkey speed and localized deployment are directly tied to the ultimate overarching goal stated near the conclusion of the proposal. And this is perhaps the most profound macroeconomic point in the entire document.
Really?
Yeah. The primary objective isn't simply to sell a specific tonnage of fiber to the GCC and Africa. The stated goal is to provide these regions with technological sovereignty and to facilitate a permanent transition to new generation industrial standards.
Technological sovereignty. That is a massive geopolitical phrase to drop into a manufacturing pitch.
It implies a fundamental shift in global trade reliance. Currently, many of these regions rely heavily on exporting raw crude oil while importing massive, expensive quantities of refined steel, aluminum, and advanced composite materials from other global manufacturing superpowers.
They buy back the finished goods?
Exactly. They are dependent on foreign supply chains for their foundational infrastructure.
But by deploying these EPC turnkey clusters locally, they flick that dynamic. They use their own local basalt rock deposits, powered by their own localized petroleum gas byproducts, to manufacture the exact materials needed to build their own cities and defense systems.
They become entirely self-sufficient in the materials of the future. It's a strategic geopolitical maneuver masquerading as a manufacturing upgrade. They insulate their infrastructure development from global supply chain shocks, tariffs, and the fluctuating prices of foreign steel.
So what does this all mean for you? It means that when you look closely at the raw materials making up our planet, the key to the next industrial leap might not be about mining some rare exotic new element from deep underground or capturing an asteroid.
Right?
It might be about entirely reimagining the common dirt and stone right under our boots. We've tracked an incredible journey today, just following the life cycle outlined in this one strategic document.
It's quite a journey.
We started with a chunk of raw, ancient basalt rock. We watched it get superheated by the captured waste gas of an oil rig. We saw it extruded into threads that can shrug off the corrosive salt of the ocean, reinforce a skyscraper from the inside out, shield a wind turbine from a desert sandstorm, lighten the payload of a spacecraft, and absorb the kinetic impact of a bullet.
All from a rock.
And ultimately, we saw how mastering that single extreme manufacturing process could rewrite the industrial power dynamics and supply chain sovereignty of entire continents.
It really is a testament to the elegance of this proposed technology. There is something profoundly cyclical and almost poetic about it. We have spent the last century pulling heavy metals out of the ground, refining them with immense difficulty, and constantly fighting their natural chemical urge to rust and degrade back into the earth.
Always fighting rust.
Exactly. This proposal suggests taking a fundamental ancient material, the solidified mantle of the Earth itself, and elevating it through applied physics. It's about replacing the fragile, heavy, high-maintenance metal frameworks our modern world is built upon with something born directly from the volcano, something that is fundamentally engineered to endure.
It certainly makes you look at a gravel driveway a little differently. Which leaves us with one final thought for you to chew on as you go about your day. If human ingenuity and fundamental thermal science can take a basic, ubiquitous volcanic rock and transform it into a $30,000 a ton aerospace-grade supermaterial that grants nations true technological sovereignty, what other completely ordinary, boring natural resources are sitting right beneath our feet right now, just waiting for the right manufacturing process to unlock their hidden superpowers? Thanks for joining us on this deep dive. Keep questioning the world around you, and we'll catch you next time.